Thanks. I'll begin. Heavenly Father, we thank you for this day. Thank you for the break that's about to start. Just to help us to use this time wisely, and just gather together ideas about how to do these integrals, Lord. In your name I pray. Amen. Okay, so the student who wrote this knew it was wrong, and I didn't let them fix it because I think it's important to illustrate when something's wrong and why it's wrong. So let's talk about this. So there's some features to this answer which should tell you you have gone down the wrong path. So the definite integral we calculate, it's representative of like a physical quantity, an area, or a volume, right? These are all numbers, unless there's some kind of other variable involved. So if your answer ends up having a variable in it, unless it's like not one of the kind of problems we typically work, that's a warning sign that you've done something wrong. Now let's see here. So the other thing is the original bounds, 0 to 1. Those essentially say that x and y are ranging from 0 to 1, both of them. And that's true. In the region that I've tried to picture, maybe that's part of the problem, I didn't put an R here, but in this region, it is true that 0 is less than or equal to x, less than or equal to 1, and it's also true that 0 is less than or equal to y, less than or equal to 1. But those inequalities do not describe that region. Those describe the unit square. Right? So if I wanted to do an integral over the unit square, I'd put this. See, I need to be a little bit more specific. Instead of doing that, I should say 0 less than or equal to y, less than or equal to x. See, because if you pick a point in here, right, x comma y, this up here is y equals x, this down here is y equals to 0, so 0 is less than y less than x. So to fix this, what we have to do is pretty simple. We just go integrate from 0 to 1, integrate from 0 to x of x, and then my y bound came first, and then dx. And then, okay, so that's xy evaluated from y equal to 0 to y equals to x, which is the integral from 0 to 1 of x squared dx. So the answer is a third. Okay, so there's that one. Any questions? So as you're thinking about the inequalities which describe your region, remember you need to get a set of inequalities that just describe your region and nothing more. The trouble with 0 less than x less than 1, 0 less than y less than 1 taken collectively is they allow points in the solution set to that system of inequalities which are not in your region. And so those are not a good set of inequalities to describe this triangular thing. Okay, let's see here. Here we've got 0 to 1, 0 to pi, don't follow the work. But I think you're, well, maybe. Y squared. I think you're right, but let me just rewrite it in standard notation if that's okay. I mean, sorry. We'll leave the answer there for prosperity. So this, I don't know. Good question. Here's a trick. When you have rectangular bounds, when you have rectangular bounds like this, right, you can rewrite the integral. There's a theorem. You can do this trick. So this is really the integral from 0 to 1 of x dx times the integral from 0 to pi of y dy. Which is 1/2 and yeah, pi squared over 2. So yeah, I agree. That's a trick. If you have rectangular bounds and your integrand factors, you can rewrite the iterated integral as a product of integrals. This is a nice thing to know about. But anyway, okay, this one here, we could use that trick again, but no need. I'm just going to do the traditional thing. So 0 to pi over 2. So we integrate the y, we get y from y equal to 0 to y equal to pi. Very good. Which gives me pi sine of x. Excellent. integrated from 0 to pi over 2, which gives me integrates to minus cosine of x times pi. I agree. And then 0 to pi over 2. So let's see here. Cosine of 0 is 1. So that's why we've got minus, but minus a minus gives me a plus. That's a pi. And pi over 2 is 0. So yeah, these are pi's. Whoa, that marker is messed up. What marker is that? Oh, which one? This one? That one's okay. This one? That one's okay. That's weird. That's like thick. I mean, it's like, I don't know. Anyway, I can't describe it. Okay, here's, are we good? Yes. Oh, please.
So it's the area of a triangle. Like, how do we receive the area of one of a triangle?
Oh, because this is not the area of a triangle. If there's an x there, so we're integrating x over the triangle. So yeah, you're right. If it was just the integral of dA, you could just say 1/2. Just like if you knew that the area of a circle was pi, you could just say that the integral of dA over this unit disk is pi. So you guys are working too hard. You could have just said equals to pi. E. Sorry. Now you're getting there. Cosine squared theta d theta. But you got to change the bounds, man. You got to change the bounds. What is, if x is equal to sine theta, minus 1 equal to sine theta, what's the half solution? What do the bounds change? Should they change to minus pi over 2? To pi over 2, yeah? And so that integrates to twice times 1/2 times pi over 2 minus pi over 2, also known as pi. If you go through the integral there. You guys were well on your way. You almost had it. You just have to change the bounds. Yeah. It's good, though. You're on. You got it. And you probably knew that the answer was pi.
Yes.
But you thought you weren't allowed to say it because you're supposed to show it.
Exactly.
And I can respect that. That's a good problem. Because I certainly will malign and harass students for the opposite thing, right? Just writing the answer down when the whole point was showing it. So I understand there's this tug of war between what the problem is supposed to be about, between us professors and you students. You know, and I've been on both sides of that issue as a student, so I feel your pain. Anyway, this one looks, I think, right. So this is a type 1. We're bounding y. Y is between 0 and, oh, that is true, that it's between 0 and 1, but we don't want to put 1 there. We want to put, oh, and we don't put 0 here either. I mean, it's true that it's between 0 and 1. I think I did that. It's not your fault, right? That was my doing, wasn't it? It might have been. But the point is x squared is down and square root of x is above. So that's why we put that here and here, because every y is between those two x formulas. That's a type 1 setup. That would be one way we can calculate the integral. Of course, I didn't even give you a function, right? So same song and dance, but for type 2, same region. So type 2, if you look at it, the left x is actually given by y squared, because if y equals x, then x equals y squared. And the right formula for x is actually given by square root of y. If you solve that for x, you get x equal to square root y. That's the right graph. And so we've got going from y squared to square root y and 0 to 1 for our y. This is the type 2 setup. Problem 6 is a pain, but I think you guys can do it. So integrate with respect to x to start with, the 1/2 x squared, which picks up, that should just change to a half, right? So we get, yeah, 1/2 yz after the dust settles. Then that gives us a 1/4 y squared integrating the y, evaluated from 0 to 2. So that should make that into a 4, should cancel the 4. We should just be left with the integral from 0 to 3 of z, yep, dz. So 1/2 z squared evaluated from 0 to 3, so we get 9/2. Excellent. Very good. This one here, I gave you the pesky unit disk. Well, not unit disk of radius 2, right? And so my only criticism here would be that you really should have a picture. You know, this kind of problem, it deserves a picture. This up here is y equals the square root of 4 minus x squared. This down here is y equals to minus the square root of 4 minus x squared, right? And so if you pick any point in the middle, right? Any point in your region, that point has y between minus the square root and plus the square root. And the x is stuck between this point, right? Which is minus 2, 0, and that point, which is 2, 0. And that's why we have minus 2 less than or equal to x less than or equal to 2, and minus the square root less than or equal to y less than or equal to the square root of 4 minus x squared, which is why we have this, whoa, flag on the play. That's a sports mention? Oh, shame. I'm sorry. I do watch the Super Bowl every year, and I think it may rub off on me after a period of years. Mostly for the commercials, but you know, I sometimes actually watch some of the game and then see then these phrases enter my vocabulary, corrupting my speech. And, oh, I tell you. So yeah, that is supposed to be f of x, y here. We are not given the formula, in fact, so that's the answer, yeah. Okay. Let's see here. This one. Okay, maybe. I don't know. Ooh, you did it as a type 2. Oh, I did. But you. Oh, but no. Not 2 type 2s, 1 type 2. Why make 2 type 2s? The whole point of doing type 2 was that you just do 1. Type 1, you have 2 regions. Type 1, you have, you know, this is y is equal to what? 1 minus, I believe, 1/3 x, right? Check it out. It's got the, 1, 1. Ah, curses. Still not right. What's the equation of this line? What was it? Well, it goes down 1 and over 2, so it's got a slope of minus 1 half x, and then plus 3 halves. Okay, so it's not particularly pretty, but there's the equation for this y. On the other hand, this one is y equals to x, right? So if you were to use type 1, you'd have different tops, and you know, you have the same. The bottom is y equals 0, right? But this has that as the top, right? And this has that as the top, with a type 1 setup. Type 2, on the other hand, if you just look at it, you know, we're going. I should really do this in something other than blue. Type 2, well, then I have a clearly defined left and right. That was the point of the instructions. Ah! You guys, why did you do this to me? It's all Ian's fault. Okay, this makes sense to me. It's all.
See, I actually knew that, but I just wanted to annoy you.
Oh, you did it purposefully. Ooh, now I respect it. Like if it was a sin of commission, then it's you know. If it's just out of ignorance, then that's different. But if it's intentional, that I respect. Yes. All right. I mean, if you understand a subject so well that you make mistakes on purpose to annoy the professor, you have reached a certain level, right? You have attained a certain level. So I'll have my eye on Ian going forward here. Now this may be right, but it's wrong. It's probably right, what I just erased, but I need to make it clear for everybody else how we should do this. And So x is, this xl is what? It's y, right? And the other one, I need to take this equation and solve it for x, and I probably just erased that. You guys tell me what it is. What's the right x if we solve for it? This, so 2y minus x plus 3. 2y equals minus x. So what did you say it was? Minus 2.
Minus 2y.
Minus 2y minus 3? Plus 3. Plus 3. So we have the following for any point in here, right? Any point x, y. Y goes between 0 and 1, right? And x goes between what? Between y and 3 minus 2y, let's say. So I would set up the integral like this, 0 to 1, y to 3 minus 2y of whatever function we're not given, dx dy. That's what I was trying to get you to do. But I think you did something that was correct, but it was just, like I probably wouldn't have taken points off on the test either for that answer you guys gave me, assuming it was correct. It's just, you're just working way, way too hard. That's the point. We talked about problem 9. By the way, future comment, integral, x squared plus y squared less than or equal to 1 dA is equal to the integral from 0 to 2 pi, integral from 0 to 1 of r dr d theta. Is how we will do this integral in polar coordinates. And that will be 1/2 r squared evaluated from 0 to 1, and then theta evaluated from 0 to 2 pi, and that will give us pi. That's how we will do it in polar coordinates after the break, all right? So you have that to look forward to. That'll make, like some of these integrals are really inappropriate, like this one too. Doing this in Cartesians is just not, it's not nice. It's much better to set this up in terms of polar coordinates, all right? We'll describe how to do that after the break. And then there was problem 10, 11, 12, 13, and 14, which are all the same problem. Twisted. I'll come back to those in a second. Problem 15, 16, and 17, they have a theme. What's the theme of problems 15, 16, and 17? So I'm integrating x over the -1 to 1 rectangle. Well, square, I suppose, right? That square. This is over the cube, which goes from -1 to 1 in all the different coordinate directions, right? So the point of these integration regions is that they're symmetric about the origin in the variable of the integrand. So when I'm integrating x, I'm adding up values of x over that area. There's an equal amount that's negative, and there's an equal amount that's positive given the integration region. So I can tell from symmetry alone, the answer is 0. Yeah. But do it with understanding. I'm just saying. I mean, you got to think through it. And likewise, this is 0 by symmetry. And you know what? That's also 0 by symmetry. But good for you guys that you worked it out. I mean, this is good practice for you at the moment. It's not wasted time at all. That you got these to work out to 0 is really good. Because, you know, the details are kind of involved, right? But I hope that also illustrates to you the power of symmetry when you can see it, right? Over here, we could have used symmetry as well. There's really no difference between any sector of the circle, right? We could have just said like 4 times the integral in the upper quadrant. You know, that would have simplified the integration a little bit. Symmetry is good to look for. All right, so let's get back to problems 10, 11, 12, 13, and 14. Problem 14, I think, is most clear. So I have a description down here of kind of what to do. The question is to integrate a function over the sort of, it's not exactly a tetrahedron, but this 4-faced solid, where the back is the coordinate planes and the top is this plane. We worked an example like this yesterday, right? I mean, I worked an example like this yesterday. No, you guys are working. So my point is, to understand that, pretty much you need to find the points that intersect with the coordinate planes 1, 0, 0, 0, 1 half, 0, 0, 0, 1/3. That governs what the outermost integration has to be, right? When I find that 1, 0, 0, that means that x is ranging between 0 and 1. So if the integration has blarg and yada and then dx, definitely the first integral, the first shall be last, it goes from 0 to 1. And this dz being last, well, the z ranges from 0 down in the base up to 1/3. So that's put a 0 to 1/3. Now, what goes on the inside bounds is complicated, and it depends on the order, whether this is x, y, or whether this is y, z. We'll get to that in a minute. Just giving you the first and most basic thing, which is you can figure out the numerical bound just from looking at these vertices. So like dy, y ranges from 0 to a half, because I know that point is where y, that point is the intersection. The y equals half plane is like here, you know. Okay, let's jump over to problem 14, because this one's good. I actually found the same, this is the answer to problem 14 actually down here. So we have x plus 2y plus 3z equals to 1. Problem 14, we do the z integration first. So the point is that if you take this equation, right, you solve it for z, you get z is equal to 1 minus x minus 2y divided by 3. So when I do the z integral first, I'm thinking 0 less than or equal to 1 minus x minus 2y over 3 less than or equal, oh, I'm sorry, idiot. Me, not you. Z, oh, wait a minute.
I mean, it would be accurate.
Sorry, that was maybe too far. I don't know. Let's see here. Sorry, okay, I must stop. So 0, z goes between 0 and that, right? So that tells us the inside bound. And then how do you figure out this 1 minus x over 2? What's that coming from? Really, that's coming from this piece right here. See that? This, if you think about extending that up and down, that tells you how x and y are related. And in particular, if I put z equal to 0, I get x plus 2y equal to 1. So if I solve this, I get, you know, y is equal to 1 minus x over 2. And that's why I put this bound here. Well, she put this bound, 0 to 1 minus x over 2. That's the y bound. That's what y is stuck between that and that. And then finally, we're back to the x, right? So let's see here. If we did the z bound last, and we did xy instead, we would have, I'm just going to write it bigger, if okay? So integrate from 0, no. Okay, 0 to 1 half, integral, and then, so the inside one is different, but the z one is still the same. So 0 to, what was it? 1 minus x minus 2y over 3. So that's my dz bound like that. I got my f. And so next comes dx and then dy. So how do I figure out how x is bounded? It's again, if I can draw a picture somewhere. There's this vertical plane with the equation in the z-axis is back here somewhere, okay? But this is the line. You put the line red. This plane is the extension of that line vertically. The equation of that plane is x plus 2y equals to 1. So we solved it basically for y to get the bound over there. We'll solve it for x to get the bound over here. X is equal to 1 minus 2y. So in fact, we put 0 to 1 minus 2y because we have the set of inequalities. We have 0 less than or equal to y less than or equal to 1 half. We have 0 less than or equal to x less than or equal to 1 minus 2y. And finally, we have 0 less than or equal to z less than or equal to 1 minus x minus 2y over 3. I mean, those three inequalities taken together, they sculpt the region down to the the tetrahedron-like thing that we have. I was told that this process is called sculpting when you cut it. I was just calling it chopping yesterday. It was told me by a certain John Phillips that I should call it sculpting, and I said, all right, fine. Sculpting seems like a good term. So there it is. Any questions? Now what was I grimacing about? I was grimacing about this. Es no bueno. No. Nah. Not belong there. Right? The function that we're integrating is given. That's what goes there. The region determines the bounds for the integration, not the integrand itself. Well, either people have rides about to come or we're out of class time, or maybe both. Have a good break.